Hello everyone, and welcome to Calculus. Today we're going to be studying the Trapezoid Rule, and after that, Simpson's Rule. You can see that I already drew the curve, so you can pause the video for just a minute and draw the curve yourself. Thought it would save us a minute here. So if we were doing MRAM or RRAM or LRAM, we would start off the same way. We would draw the sides of our rectangles. And then if we were doing RRAM, we would start on the right-hand side. We would attach it to the rectangle to the right-hand side of the curve. If we were doing LRAM, we would attach it on the left. And if we were doing MRAM, we would go up to the middle and then make our height. And of course, we learned that MRAM definitely made the best possible answer. Now, in this case, we're going to be doing something a little bit different. We're going to be making trapezoids. So in case you didn't know what a trapezoid looks like, this is your general shape of a trapezoid. That's how people think of it. But it actually can have one flat side and still be considered a trapezoid. So why don't we always use trapezoids? Because look, if I make a flat-sided trapezoid, I'm going to do this exact same thing, but I'm going to turn it upright. So there's an upright trapezoid. Look how nicely that follows the curve, right? These trapezoids are fantastically close to the curve. Even though I only did 4 of them, it's going to give me a really great estimate. So why didn't we do trapezoids before? Because they have a really annoying formula. Unlike a rectangle, that's just length times width. In this case, I need to average the bases and then multiply by the height. So if you didn't already know the formula for a trapezoid and you're going to have to memorize it, I would actually memorize it differently. This is how every book writes it, but I think it's easier to think of it as base 1 times base 2 divided by 2. In other words, move the 2 over here, because what you're really finding is the average of the bases and then multiplying by the height. And I can show you really easily on this one. This is base 1 and this is base 2. If you average those lengths, you get something somewhere out there. So what they're really doing is making a rectangle, and they're doing the average base length times the height, which of course loses some area that's not counted, but then it gains some area that's the exact same size. So that's how you find the area of a trapezoid. So it's a little bit more work for us. So our estimate for the area under the curve is going to be 4 trapezoids. 1, 2, 3, 4. The first one is going to be, now remember, this is a sideways trapezoid, so the base is base 1, base 2 divided by 2. So it's going to be 2 plus 1 divided by 2, and then times its height. Now, height is a deceiving word, because if we flip this on its side, the height is actually going to be along the bottom, but that's the way to make it fit our curve. So the height is 1. And then our next one also has a height of 1. They're all going to have a height of 1. This is the height each time. You have to kind of turn sideways to see that. And then this one, base 1 plus base 2, is 1 plus 2. And we're going to average those. And this one is 2 plus 5. And again, we're averaging those bases. And this is 5 plus, what is that, 10 over 2. So we get 3 halves plus 3 halves plus 7 halves plus 15 halves is, what do we have there? 22 plus 6 is 28 halves, which is 14. You may remember from when we did this problem in the past, I think the answer was 13 1/3 if you did it by exact integration. So is it close? It's fantastic, okay? And you can see that it overestimated the curve just a little bit. Now, if you think about it, in every single one of these trapezoids, I multiplied by 1. In every single one of these, I divided by 2. So somebody smarter than me came up with a formula for the trapezoid rule. They said, look, let's factor out that h. And that's where this is. They took that h out and they took the 2 out. And then they said, you're going to have this height right here just once. So they call that y0. That's the first base. But then the next one, it's right here. But then the next one, this red one, that's part of the first trapezoid, but then it's the first base on the next trapezoid. So that's where they got 2 of the next y value. And then this one is the end of the second trapezoid and the beginning of the third trapezoid. So that's where they got 2y2. And so it continues until the end. This last one is only part of one trapezoid, just the end one, and that's why it only got written once. That's where that formula comes from. And then you'll notice that they have h is b minus a over n. So it's this distance right here, but it just depends on your total distance. So we're going from -1 to 3. That's going to be 3 minus a -1. So a distance of 4. You don't actually need to do that math. You can just look at it and see that it's 4. And then we did 4 subintervals. We did 4 trapezoids. So our height, remember this is called the height because it's a trapezoid on its side, was 1. If you find the trapezoid rule confusing, you actually can just average LRAM plus RRAM. That will give you the same thing as the trapezoid rule. The trapezoid rule is not the same as MRAM. That actually does give you a different answer. To go to 2.5 and then go up like that will give you a different answer. But the trapezoid rule is equal to LRAM plus RRAM. When the curve is concave up, the trapezoid rule is going to overestimate the actual area because the trapezoid will go from tip to tip. But when the curve is concave down, like that, when we make that into a trapezoid, you're going to lose some of the curve. So it's going to underestimate the area under the curve. Okay, let's try an actual problem. So an observer measures the outside temperature sporadically from noon until midnight, recording the temperatures in the following table. What is the average temperature for the 12-hour period? So normally, if you were going to find the average, you would just add them all up. So 63 plus 65 plus 66 plus 70 plus 69 plus 65 plus 64 plus 62 plus 55. 1, 2, 3, 4, 5, 6, 7, 8, 9. Divided by 9. And if you just add them up and divided, I'll do the math for you, it would come out to be 64.3. However, let's make a graph and I'll show you what happens. So we only really need to get from, so I'm going to make one of those little, like, I'm not including part of this graph. So the lowest number that we have to get to is 62. So I'm going to call this noon, and then at 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, I'm skipping, and midnight. So 63, 65. We've talked about this before. You don't really need to have an exact number. You're just trying to get a sense of where it's going. 70, 69, 65, 64, 62. Oops, I missed that. We do have to go all the way down to 55. Okay, so I'm going to make my trapezoids. you actually can't use the formula that I just spent a few minutes teaching you how it works. So this formula only works when you have equal length intervals, like we did for this first one. This one does not have equal length intervals. So you're actually going to have to do every single trapezoid separately. So trapezoid 1 is going to be a height of 1, this is 1, times 63 plus 65 divided by 2, plus trapezoid 2 also has a height of 1, is going to be 65 plus 66 divided by 2, plus trapezoid 3. Ooh, this one has, you see this? 2. 66 plus 70 divided by 2. This is the average of these two bases times the height. That's what a trapezoid is. Average of the bases times the height. Trapezoid 4 also has just a height of 1, and then it's going to be 70 plus 69 divided by 2. It's always divided by 2 because that's the average of the two bases. Plus trapezoid 5. This one has a height of 3. Make sure you catch that. And then 69 plus 65 divided by 2. Plus, this is a 1, 65, I know this is very tedious, over 2. Plus 1, 64 plus 62 divided by 2. And the last one, plus, this one is 2, has a height of 2, and this trapezoid is 62 plus 55 divided by 2. Okay, so unfortunately, I know that you are just sitting there waiting for me to add this up, that you're not going to take out your calculator and do it yourself since you're home. So I will add it up for you. And when I do that, I get 780.5. And at this point, you might think you've made a mistake because obviously this answer is nowhere close to my 64. That can't be the average temperature. But remember what you're doing. You're finding the average value of the function, right? The average temperature. Do you remember learning average value recently? Average value is 1 over b minus a times the integral. So the integral adds it all up, but you still need to divide by this distance. So this is pretty much 0, this noon, and 12 hours have gone by. So 780.5 is the total divided by 12. That gives me, let's see, 65.042. That's the number that you want to compare to the average that you got otherwise. So you might be thinking, what does this even matter? Who cares how close it is? Well, it depends on what you're doing with it. If it's just for casual purposes, you probably wouldn't do any of this regardless, even the simple average. But if you're a scientist and you're studying something where knowing the best possible approximation for the average temperature is important to you, then you're going to want to use the trapezoid rule, even though it was more tedious. Okay. All right. So there was this guy named Simpson, super smart. I do not remember anymore how he came up with this rule. I'm sure I had to learn it at one point. But I'll just tell you that he literally took the trapezoid rule and he tweaked it. You know, this is before internet, Facebook, Instagram. He had all the time in the world to sit around and say, you know what? I think I can make that even better. So somehow he figured out that if he took the height, instead of dividing by 2, he divided by 3. And every other one of these 2's, he changed to a 4. He figured out that he could make a super amazing estimate. It really is very impressive. You do have to have this work out so that it comes out to a plain 1 in the end and then 424. So we're going to use 4 subintervals to do this. So sine from 0 to pi You know the sign goes like this, but we're just going to look at this one section. So here's pi halves, pi fourths, 3 pi fourths. If we did it by trapezoid rule, we would get a pretty nice answer, right? It's not going to be that bad. But Simpson tweaked it. He figured out a way to make it even better. First, let's calculate all of our y values. At 0, y is equal to 0. At pi fourths, y is the y value, so that's going to be a base. But that y1 is going to be the square root of 2 over 2. Sine of pi halves is going to be 1. Sine of 3 pi over 4 is also going to be square root of 2 over 2. They're at the same height. And then our last one, y4, it goes back down to 0. So Simpson's rule says you can take the height. So how high, luckily these are all even intervals, so you can use Simpson's rule. They're all pi fourths divided by 3. And I'm going to do y0 plus 4 times y1 plus 2 times y2 plus 4 times y3. And then we're at the end one, so you would keep going in that pattern, but once you get to the end one, then you just leave it plain, plus 0. So this gives us pi twelfths. That's not 12. That gives us pi twelfths. And then this is 2 square roots of 2 plus 2. And this was also supposed to be a square root of 2. And this is also 2 square roots of 2. And I don't know that I can do very much more with this without my calculator. So I'm just going to go ahead and type it in. And it comes out to be 2.00456. So what is the exact answer? I don't know if you remember this from an earlier lesson, but the straight up integral from 0 to pi of sine of x is 2. So he was literally right in his estimate within 4 thousandths. Very, very, very impressive. I will not take the time to do n is equal to 8, but I will just tell you that the answer is 2.000026917. So 4 intervals really didn't take us that long. 8 intervals would be harder because you don't know off the top of your head what sine of pi eighths is. So you'd have to do it all on your calculator. But look at that. Look how fantastically close that answer is to the real answer. All right, you should really try, I'm always saying this, one of these on your own. I will tell you that the answer is 32 1/12, or 32.083 repeating. The real answer is 32, which, this is supposed to be a 12th, which means his estimate using only just 4 rectangles is only off by a 12th. Again, a fantastic estimate. So in case you still are not sure how to do this on your own, we can do it together. We're doing 5x to the 4th. So when you plug in a 0, you get 0. Now we're only going up to 2, but we need 4 subintervals. So we're unfortunately going to have to plug in a 1/2 and then a 1 1/2. So if I plug in a 0.5, so let's see. I know you're not doing it. I know you're waiting for me. It's so sad. All right, so when I plug in a 0.5, I get 0.3125. It's really small. 0.3125. When I plug in a 1, obviously, I get 5. It shoots up pretty fast. When I plug in a 1.5, I get 25. It's really growing fast. 25.3125. And then when I plug in a 2, I get 80. So this is really steep curve. I didn't even begin to draw it steep enough. But it gave me the numbers that I needed in order to do Simpson's. So Simpson's is the height, which is 1/2 divided by 3 times the first y value plus 4 times the second y value plus 2 times the third y value plus 4 times the next. Notice I keep going 4, 2, 4, 25.3125. And then nothing times the last one. That one gets to be by itself. And like I said, if you do this out, you will get 32 and 1/12, which is just super amazing. For AP students, I just want you to know I have, despite it being in the list of things I'm supposed to teach you, I've never seen Simpson's rule on the AP Calculus exam or even on a practice exam for that matter. But what you will see a lot of is trapezoid rule with different intervals. They want to make sure you actually understand how the trapezoid rule works, why this 3 is there, more than just can you memorize this rule. They want to make sure you understand how it works, and they're going to do that by using different intervals. But Simpson's, never seen it. All right, have a great day.